Hi everyone. Because I couldn't see the room, so I couldn't hear the room. I don't know how many of you guys there. So I'm an independent researcher from Malaysia. So today I'm going to share a small, weird, little experiment that I've been doing with Lean 4. So it's called Gödel mirror, where the logic is the logic system where logical contradiction don't explode, but instead they get metabolized into structured states. So there's a versions of this paper I published on archive preprint server. So in case you guys are interested, you guys can check it out. All right. So what's the motivations for the work? So the motivation for this work is that I find that in LLM or all the modern neural network, contradiction I think is inevitable, because as a active user for ChatGPT, I find that they often contradict themselves. So in classical logic, a contradiction usually lead to explosion. So anything can be proven. So Gödel also say any advanced system that can self-reference, eventually there must be a true statement that cannot be proven within a system. So I flip it to make the contradiction as a first-class citizen of Gödel mirror. So I asked, can we metabolize the contradiction as a part of the computation? So in this slide, I show the Gödel mirror mechanisms in one slide. So basically, when a self-reference contradictions arise, we call it paradox. So it doesn't explode the system because it got encapsulated and put into a capsule. Then it re-entered into the reasoning state and get metabolized into a stable node. So the key idea is that we take the contradiction and we make it explicit within the system. And we start to do the recursion. So maybe I show you the code. So basically in Lean code, I define two inductive type. One is a mirror system. So here are the cases, base cases, node, self-reference, encapsulate, re-entered, and name. And then we also define the possible states of the mirror. Basically, we got normal, paradox, integrate, and re-entry. So this mirror state will be used by our classified function to decide whether the term is in which state. Then we got our reduction functions, which is single step reduction. And we got the run function, which is basically a multi-step reduction function. Just run through the step over the n times. So okay, I think I didn't go to the next slide. So basically, this is our inductive data type in the Lean. So here is the demo for a liar paradox. So basically, let me go back to the code. So basically, in the Lean code to demo this liar paradox, I make the function liar and make it self-reference. So this is a liar paradox. So once the contradiction got detected, then we encapsulate it into step one, and then we re-entering into the re-entering stage, Then eventually on step 3, we will turn it into a stabilized node. So there are also other demos like nested paradox, which is a paradox within a paradox. So we also have simple self-reference, which is basically a simple form of paradox. So basically, what the code does in the so basically this is the info view. So at first we detect the paradox, then we encapsulate it, and then we re-enter the paradox into the system, and then we stabilize it as a node. Then we'll keep wrapping the paradox into a node. So at stage 4 and above, eventually it will stabilize as a node. So another insight is that for the nested paradox, so basically this is a contradictory statement, but the Gödel mirror always process the outermost label first. So this is a feature. So eventually, the Gödel mirror system is about a 3-step cycle as a structural invariant. So we detect a paradox, we encapsulate it, and we re-entry, and we stabilize it as a node. So key properties demonstrated is Gödel mirror is always deterministic, always the same transformations, and no logical explosions, and universal and verified in Lean. So here comes the proof part, which is the formal verification, because just now I showed the mechanism, how Lean actually works. So from the insight, we have the step function step by step and process the outermost paradox one at a time. Then in this workshop, I also use a trick called field evaluation, which is basically just a trick to demonstrate to peek inside the completion behavior. Because in order to prove a system to complete is actually quite challenging. So later I will talk about this. And the key insight is that the self-reference constructor is actually irreducible. So it's always deep inside the tree structure. And doesn't matter how deep it is in the tree. So the self-referential paradox is always there. So by design, Gödel mirror doesn't solve paradox. It metabolizes them into a stable structure that don't explode the logic. So 3 theorems that I prove using Lean. So progress for any terms, it either has a value or they can take a next step. And there's non-explosion theorem, also proven in Lean, and there's labor preservation. So maybe we can take a look at the meta theory. So this is a progress, which means it either has a value or they can take a next step. Then also we have a control reaction to paradox, which is one of the main theorem that I published in the paper. And then we have the labor preservation, which means the labor always preserved after all the transformation. Okay, so for the completions, I use this field evaluation techniques because just to show you guys how it looks like when the Gödel mirror complete computations. So anyone interested, you can check it out in examples.lean. And basically before the computation is the liar paradox got detected, then it will wrap into a node. So this is after the completions. And then the paradox is always there. So this is our feature. So what I do this completion using the tricks instead of the actual proving is that to prove the termination is actually very hard, at least at this stage using Lean. So in order to prove the termination, right, we have to define the complete as an induction relations and prove that is well founded, and prove the confluence, and prove the termination. So this is the proof part, and it's the most challenging part. So here comes the takeaway. So why I use Lean 4 in the first place, because I find that it has all the things that I need. Precision to define my type, and then I can have my functions, and then I can execute the program, and I can have the proof built in. So what is still hard is that the non-termination, because at current stage the Lean function assumed to be terminating, so it must be total. If I use the partial function, it actually breaks the principle of induction. So for this workshop, I use the field evaluation. Basically, I assign a fixed limit how many runs to complete the program. And then for proof, which is still work in progress, I might use some small step relation semantics to actually do a proof, so that LMCS guy can actually do the formal verification when they review my work. So why it matters for Lean is that why Gödel mirror matters for Lean is that it's a non-terminating calculus, and also we can use the field or relational semantics to do the completion. But this is just for demonstration purpose. But for community, I think Lean still lack of term rewriting library. If anyone aware, you guys can give me a pointer. So yeah, if with the term rewriting library, the LMCS guy can review my work and also see it, how it's actually be automated proven. So likely I will be very happy to see if any new TRS library for rewriting researcher. So conclusions, Gödel mirror system doesn't with contradictions, it doesn't explode, but it get metabolized into the computational node. And Lean helped me to make this real, because I am an outsider. I'm not even a Lean coder, and I'm not being trained in formal methods. So Lean allows me to do all this experiment to propose a new computational model that use contradiction as a computational subject. So I guess that's it.